Hi, I'm Fred Dillon, and we're going to be looking at lines of fit. This is data that was collected by the United States government that shows that the average weight of a man increased from 1960 to 2002 from 166.3 pounds to 191 pounds. Since this is bivariate data, two sets of data that are possibly related, we want to see what the relationship between the two data sets is. The first step is to graph the data to see what pattern seems to exist. The graph of the data points is called a scatter plot. You need to get a graphing calculator so you can follow along. On a graphing calculator, we go to the Stats menu, then to the word Edit. We then press number 1 and go to the lists. You can use the following keystrokes to begin entering data. Press Enter after each data point. To get a graph that fits the data points, we need to get to the data graphically. To do that, we will use the y equals stats register and use these keystrokes. Second, y equals. The keystrokes are how to access the stat plot function. We are setting the calculator to graph the years after 1960 as the independent variable and the weight as the dependent variable. After we have all of these things set, we are going to go to the stat plot. We need to set the scale first so that we can see our graph. The easiest way to do this is to use a function called zoomstat. To access that, just press zoom number 9. The calculator will display this graph. The scatter plot shows a strong linear association. A different view of the graph can be made by changing the scales or using a different capability. Here is an applet that also graphs scatter plots. This view has the added quality of a visible scale and allows us to make a manual line of fit. A manual line of fits means that we draw a line that seems to fit the patterns just by our view. This is also called a visual line of fit. This applet will allow you to put a green line that you can drag till you think it fits well. At that point, it will give you an equation for that line. In many cases, a visual line of fit is sufficient to show simple predictions about the data. You just want a graph that looks like it fits well amongst all the points. There are other methods of finding lines of fit that allow more analysis of the data. The most commonly used line of fit is the least squares regression line. I will frequently refer to this as LSRL. An applet is available at this address that we will use to help us find this line. It illustrates how the least squares regression line is calculated. A line of fit is drawn so that the square of the distance of each data point to the line is minimized. Squaring is done so there is no sign on the differences. Without squaring the numbers to make them all positive, a set of very large or small differences would have a small sum close to 0, even though the line of fit was not close to the data. This picture shows how the squares are drawn, and you can see across the bottom how the summing of those square differences is made. Here is a picture where the squares have been minimized a bit, resulting in a better line of fit. To calculate the least squares regression line, we need several statistics. First, we need the mean of both the independent x and dependent y variables. We will call these x bar and y bar. The next statistic is called the correlation coefficient. This is used to measure the strength of the linearity of the data. The correlation coefficient is labeled R. When data is perfectly linear, its R value is 1 or -1. When data has absolutely no linearity, it has an R value of 0. Mathematically, we say the closer the absolute value of R is to 1, the better the linear fit. How do we calculate R? Well, first, we need to ensure that even when x, y values are from widely different sets, the relative sizes of the data will not affect the R value. To take care of this, we center the values to 0 and remove the effects of relative size. This is very similar to standardizing a variable in a set of data. To center the data at 0, we're going to take each data point and subtract the mean of the data from it. Recall the mean is the balance point of all data, so this is recentering our data from the mean as a balance point to get 0 as our new balance point. To remove the effects of relative size, we're going to divide each value by the standard deviation of its data set. You can see here the quantity x minus x bar over sigma x and the quantity y minus y bar over sigma y. It is important to realize that each x value that has the above mean produced gives a new value, and that while each x value that was below the mean produces a negative new value, the same will be true of y values, and being above will produce a positive new value. The mean of both the x and y values are increasing as the data pairs move to larger and larger x values, but new values are positive. If x is decreasing and y is decreasing, the values will eventually be below the mean values for each data set. In this case, the new values will be both negative. If x is decreasing and y is increasing, the values of x will eventually be below the mean, and the values of y will be above the mean. In this case, the new values will have opposite signs. The same occurs when x increases and y decreases. The new values have opposite signs. Taking the product of each corresponding new x value and its matching new y value will give us a set of positive and negative numbers that show a point's position in relation to the mean of x and the mean of y. We want to quantify the relationship and find its value. We take the sum of the product of each x term and each y term and write the formula this way. This is sigma notation. That means we're going to take a sum of each of these things as I progresses from 1 to whatever number we have for n. X sub I minus x bar over sigma x could be the first term, x1, the second term, x2, etc., and then we add them. We are almost done. We now average these values by dividing by the quantity n minus 1. This is the statistic used so that we have what's called an unbiased estimator. If r is positive, both x and y travel in the same direction. That means as x increases, y increases, or as x decreases, y decreases. In both cases, the line has a positive slope and rises as data values move from left to right. If r is negative, x and y travel in negative directions. That means as x increases, y decreases, or vice versa. In both cases, the line has a negative slope and falls as data values move from left to right. Now we can measure the strength and direction of our linear fit. Be aware, outliers can have a very strong effect on R as it is created from the mean and standard deviation, both of which are easily influenced by outliers. One point far from the rest of the data set can make R seem abnormally high or low. We are ready to create the least squares regression line. The minimizing of the squares of distances from the mean forces our line of fit to go through the means. That is, x bar, y bar must be an ordered pair on the least squares regression line. The slope of the line is determined by multiplying the correlation coefficient, r, times the quotient of what could be viewed as the change in y over the change in x. It truly isn't that. It's really the standard deviation of y over the standard deviation of x. We now have that the slope, m, equals the correlation coefficient, r, times sigma y over sigma x. Since the least squares regression line contains both means, we use point slope form to find the equation of our line of fit. That is, y minus y bar equals r times sigma y over sigma x times the quantity x minus x bar. And we can rewrite that as m times the quantity x minus x bar. Using the distributive property, we have mx plus negative m times x bar plus y bar. Those last two terms are a constant, which we usually rewrite as b. You can see mx plus b, or on most calculators you'll see it written as ax plus b. This is the calculator readout for our data. You can see it says linear regression, and it has y equals ax plus b. We write y hat is approximately equal to 0.573x plus 165.455. The y with the caret over it is called y hat, and is a symbol that generally indicates that we're using a least squares regression line. In this picture, we can see that after 0 years, we would expect a weight of 165, which was close to our original data. We can also see the slope is around 0.6, which means that for every year of increase, we anticipate an increase of 0.6 pounds per year. To look at the weight in 2010, we will be looking at 50 years after 1960. We would do this by predicting with our line and using 165.455 plus 50, the number of years, times the slope, and result in an average weight in 2010 of about 194 pounds. Keystrokes to find the least squares regression line and to store it in your calculator are as follows. You want to go to the Stat menu, and you want to then list L1 and L2. The last step has y sub 1. To find that, you have to press vars, arrow over, press number 1 to get function, and press number 1. The screen will result in that entire equation moving into the y1 register, so you have all of the decimal places, and you can then graph the line so you can see it against the scatter plot. We have learned today to plot data and to find a line of best fit for prediction if the data is linear. We have also learned to calculate the correlation coefficient and the least squares regression line by hand and with technology.